Okay, we will start then. And as I said, there is a part of the unit second which was in fact left behind in the recurrence relations. So I have shared some of the material to you in the group yesterday, and I will repeat it again that the excluding the greedy approach, everything including the recurrence will be in the syllabus for your internal first. So there was this mathematical part. Actually, this is not the computer science core part, but this is the discrete mathematics part. To solve the recurrence relation using some other methods. So we will have a look on it because it has been also included in the syllabus. Please maintain the gap. Some of you come here, some of you sit there. So there is this concept of homogeneous, non-homogeneous recurrence relations. Okay, and a relation could be either in any one of the form. It could be in homogeneous, it could be in inhomogeneous form, based upon how their how that equation or relation is possessed of. Like in the linear algebra mathematics, we say the linear equation is quadratic based upon the the power of the respective variables and the coefficient terms. So accordingly, the recurrence relations are also divided into homogeneous and non-homogeneous. Then the type of power which they are having, suppose if it is linear, that's known as linear homogeneous. If it is quadratic, then it's known as quadratic homogeneous. Likewise, on increasing the power, the respective terminology changes, and this applies to both homogeneous as well as non-homogeneous recurrence relation. Means homogeneous will be of linear type, it will be of quadratic type, it will be of cubic type. Non-homogeneous will be also of the same type. But what we are interested among so many types of these recurrences will be in this topic will be homogeneous and that also linear in nature. That is the first one. Okay, so we will deal with the homogeneous recurrence relations. Homogeneous recurrence relation of linear nature. So it is a three-step process. Just remember or understand what we will discuss here. It is a three-step process to solve such recurrences. Okay. The first step is that there is a general pattern or there is a general equation by which we are able to understand in which form this recurrence is. There is a general polynomial you can say, and that polynomial is of the form a0 f of n plus a1 f n minus 1 plus a2 f n minus 2, and this goes on until we reach to a n f n minus k. This should be equal to 0. So we have to compare our recurrence relation which is given to us. The recurrence homogeneous one which will be given to us to find it a solution. The first step we have to do is compare it with this general polynomial form in order to see find the values of these various terms, various coefficient terms. This is the first step, that we have to compare that recurrence with this polynomial. Okay, so I will I will go slowly so that this will get understandable to us. Suppose a recurrence is given to us f of n that is equal to n if value of n is either 0 or n is equal to 1. This is a recurrence which is given to us. The second is it is f of n minus 1 plus f of n minus 2, and the condition is given that when f n is greater than 1. Maintain the gap, and you are welcome to be offline here, but please maintain the gap. So here is an example of an homogeneous linear recurrence relation. Fine. So what we need to solve is we need to go to this very direction in which the n terms keep on repeating. Okay, this is a kind of recursive function. We decrease the function each time by a parameter. So what we will do is that we will write this part of the recurrence equal to f of n equal to f of n minus 1 plus f of n minus 2. Some of you come here in this direction, in this side, please. So we can write it like this also, because this is the one which we have to solve. Yes, and if we write it f of n, we will take it on this side, f of n minus 1. This will also become minus f of n minus 2. That will become equal to 0. Okay, till now it's clear. So what we will do is we will now compare this standard form. This will become the standard form of our particular recurrence. That is this one, which we have taken as an example. So what I said is that the first step to solve such type of homogeneous linear recurrences is to compare it with the fundamental form of this recurrence which is given to you. So when we compare it with this, we will get the values of different coefficients. Like the A0, A0 is the coefficient which is multiplier to the first term. That will be equal to 1. In the same way, A1 will be equal to minus 1. That is the one which is multiplier here. Similarly, A2 will be equal to minus 1 here. Okay. And one more value which we are interested in, that is K. K is the total levels which we have, the total number of levels in this recurrence to which we are expanding this. That is, we are going from level here 1, 0, 1, and 2. So the total highest number of the levels where we are expanding this recurrence, that is the value of K. So we are going to the value 2. So K value will be equal to 2 here in this particular recurrence. Okay. So till now we have been able to find the values of these few coefficients by comparing our recurrence with the standard one. This is the step number first. Now the step number second is that there is a polynomial solution given to these recurrence homogeneous linear relation. There is a polynomial which is given, which becomes the solution for these type of recurrences. And that polynomial is, I will write it here, A0 x power k plus A1 x power k minus 1 plus A2 x power k minus 2, and until we reach to the point an x power k minus 1 equal to 0. Okay, this is the solution of polynomial solution of the recurrences which are in the form of both homogeneous as well as linear. So the values which I got from the previous step, that is the step number first. If I put those values here in this general polynomial solution of these recurrences, what I will get is, in place of A0, it will be 1, x power k will be 2, yes, plus, then in place of A1, it will become minus 1, x power 2 minus 1, k minus 1, plus A2, A2 is equal to minus 1 again, x power k will again become equal to 2 minus 2. Only till this I am having the term, so I will equal it to 0. So my recurrence will take the form x square minus x power 2 minus 1 will become equal to 1. This will become minus x power 0, it will become equal to 1, that should be equal to 0. And this will now get converted into a form which will become a quadratic equation. So it's not recurrence, it's now equation. Okay, so this is the second step. The third step is here. Here I have got the mistake. It is not, it is equal to ak equal to 0, the general polynomial term. So when I am having the quadratic equation, so I will solve this quadratic equation in order to get the two roots from it. Okay, the solution will be, if I had to do splitting of middle term or I had to find a discriminant. These are the two term ways to solve it. So to find minus b plus minus under square of b square minus 4ac divided by 2a, that will be the solution. So minus b mean is equal to what? The coefficient term which is attached to it or multiplied to it, plus minus under root of b square, that will again become equal to 1 square, minus 4a means 1 and c means minus 1 divided by 2 into this is multiplied by 1 and it will become equal to 1. So this will be 1 plus minus under root of 1 square plus 4 divided by 2. So my x1, I will represent it x1 or x2, the two roots, the two values of x which I get. At one it will be plus and the other time it will be minus. Let me keep it here as such. Now I will go to step number 3rd. As I said, there are 3 steps to solve such recurrences which are of the homogeneous linear nature. And the final solution of such recurrences is given by f of n is equal to C1 R1 power n plus C2 R2 power n. This is the final solution of such recurrences. And now don't ask me where from I have got this. This is all discrete mathematics. Okay. I can't go into detail of all this because you have to only a part, sub part of this is given to you to find the proof why this. There needs to get a doctorate for it. So now this R1 term and this R2 term. R1, out of this solution, we have got C1, R1, C2, R2. So if I know the values of all those variables, I can simply put it in this equation and this will be the solution of my original equation which I took equal to f of n is equal to that recurrence relation. So this R and R1 and R2 are these two roots. The two values which I got after solving the quadratic equation. So in place of R1, we will substitute 1 plus under root of 5 divided by 2. In place of R2, we will substitute 1 minus under root of 5 divided by 2. Now the only thing which is remaining here is the C1 and C2. Okay, and C1 and C2 values are found by taking initial conditions into consideration. Initial conditions. And what are those initial conditions? Initial conditions are that my whole recurrence was equal to f of n equal to n if n was either equal to 0 or it was equal to 1. And my f of n was equal to f of n minus 1 plus f of n minus 2 if n was greater than 1. So taking initial values from it, the first initial value will be what? If I put n is equal to 0. Okay, if I put n is equal to 0, in this equation. Let me name it as equation number A. In equation A. So what will it become? This will become f of 0 in place of n. Okay. And on the right hand side, this will become C1 R1 power 0. This will become C2 R2 power 0. So moving forward, this is f of 0. This will become equal to C1 plus C2. But f of 0 is equal to what? When n is equal to 0, this will become C1 plus C2 is equal to. I think there is what is this doubt? If n is equal to 0, okay, yes. When n is equal to 0, the value of f of n is equal to n at that very time. Since n is equal to 0, which means f of n will be 0. And when n is equal to 1, f of n is equal to 1. So it will be equal to 1 at that time. So it's right. We will keep its equation number as B. Now taking the second condition, second initial condition, this was the first initial condition. And what was the first initial condition? We took n is equal to 0. Now we will take n is equal to 1. Okay. When we took n is equal to 1 and substitute in this equation. So this will become on the right hand side, it will become f of 1 is equal to C1 R1 power 1 plus C2 R2 power 1. Now when n is equal to 1, f of 1 is equal to 1. This will become C1 R1 plus C2 R2. So let's keep this as equation number. So R1 and R2 values I already know. Okay, because we have taken those equal to the R1 values we have already calculated from here. As I said, R1 is equal to this one, R2 is equal to this one. So if I do one thing, if I take this equation number C, it is equal to 1 C1 R1. In place of C2, I can substitute the value equal to minus C1 R2 from equation B. So this will become equal to, I can take C1 as common, R1 minus R2 will become equal to 1. So this will be equal to, C1 will be equal to 1 by R1 minus R2. And I can substitute the values of C1 is equal to 1 divided by R1 is equal to 1 plus under root of 5 divided by 2 minus R2 is equal to 1 minus under root of 5 divided by 2. This is what it was. So on solving it, what will be its value? Please solve it, somebody. Is it the final answer? Okay. And C2 will be equal to, okay. Now when we have found the values of all the coefficients, so the final solution of such recurrences will be C1 R1 power n plus C2 R2 power n. On substituting the values here, f of n will be equal to C1. In place of C1, it will be under root of 5. R1 will be equal to the value which we got on in the previous, that was equal to 1 plus under root of 5 divided by 2 power n plus this will become equal to minus under root of 5, and in place of R2, 1 minus divided by 2 power n. That will be the final solution of such recurrences. This is pure mathematical, okay? Any doubt in it? Okay, and please open your rough copies, and there is one more equation of the same pattern which will be given to you for solution, and that is P of n is equal to 0 if n is equal to 0, 5 if n is equal to 1, 3t n minus 1 plus 4t n minus 2 if n greater than 1. So the students who are online, please solve this recurrence as per the previous one and update me regarding the results. The pattern is same which we used in this recurrence. This is the basic polynomial. Compare the recurrence relation which you will get from this example and with this one to find the values of a's. The first step. The second one is to put the values in this polynomial to make it a quadratic equation. Third step is to put the values obtained in the first two steps in the equation. Done? Yes. So actually we're solving this recurrence to find its complexity. The final goal is to bring it in a form by which we'll be able to see its growth of the function. And you see, the growth of this function is also kind of exponential into the power of n. Our previous recurrence were also of the same type. Okay, the online students have been able to solve it.
Yes, sir.
Okay, write down your. Okay, tell me what's the answer.
Sir, T of n is equals to 4 raised to power n minus 1 raised to power n.
Okay. CR. Okay, pay attention now. Overhang the situations of the recurrences of type test. We have studied this so many numerous number of times. And inside that, we said that the program segment is of the form. Initially, we started with n greater than 0. Then we started with n greater than 1 in case of dividing functions. Now we will start with n greater than 2. And inside this if condition, there are some statements to be executed. Then it's closed and a recursive call is made to the original function, but in the form of its under root. So initially, if we were passing n equal to 25, so now we'll be passing its under root of value. Okay, and that will be only equal to 5. So we are recursively calling the function. It becomes a recursive call, and the parameter value also decreases. But the way it was decreasing in case of dividing functions and the way it was decreasing in case of decreasing function is different here in case of this under root 1. So such type of solutions or such type of the problems are solved by changing the variable. Okay. So if we take this example to understand this concept of change of variable, so we will use the benchmark techniques which we have studied so far. So the total complexity of whole this algorithm will be taken equal to T of n. And this statement, it will be executed for once at a particular time. As usual, we will take it equal to 1. And the instantaneous characteristic is described by this under root term. The number of terms the recursive call will be made, that will determine, let me take its time equal to T under root of n. Okay. So if I now convert it into a recurrence relation as we were converting initially, so the conditions are 2. T of n, that will be either equal to n is equal to 2 or n will be greater than 2, the two conditions. And I am saying when n is equal to 2, take any constant value. The condition is checked only once, then it does not do anything. Okay. Now when it becomes greater than the value of 2, at that very time, the total time it will take will be dependent on the instantaneous characteristics, that's T of under root of n, plus this simple constant program step. While solving such type of recurrences which come in this form, we use this technique. And the solution means to go to this part. Once we go to this part and try to see what will happen, we will write this recurrence here, T of n equal to T under root of n plus 1. So T of n will be equal to T taking under root in terms of powers, it will become 1 by 2 plus 1. Okay. So now my recurrence has come into standard form. So I will use the substitution. I can use any method. Let me take the substitution method. What I do in substitution is that I say that if I know the value of n power t n power 1 by 2, I will substitute it here and I will see what will happen, what will be the result look like. So in order to find the value of t of n power 1 by 2, what I will do, this is my original standard form first. So I will write it here again, t of n power 1 by 2 plus 1. So to find the value of t of n power 1 by 2, that means that at place of n, I need to substitute the value n power 1 by 2. This I have to substitute in place of this. And this 1 by 2 is already from the previous step. No doubt, then this plus 1 is already here. Okay. So that means t n 1 by 2 square plus 1, and this will become my n t n power 1 by 2, this whole. So once I substitute, take this value from this equation, put back in equation number 1, I will get t of n equal to, in place of this t n power 1 by 2, I have to write this whole. So this will become t n power 1 by 2 square plus 1, this, then plus 1 is from here. That means t of n will become equal to t n 1 by 2 square plus 2. So again, by using the substitution method, I will see that if I know the value of this thing, I will substitute that in this equation. Let me name it as equation number 2. And simply, if I follow the same approach, t of n power 1 by 2 square, that will be equal to t of n. In place of 1 by, I have to write 1 by 2 square into 1 by 2 is proper formula itself. Okay, plus will be 1 from the formula again. So again, resubstituting it here, I will get t of n equal to, in place of this whole, it will be t of n to the power 1 by 2 cube plus this 2 plus this 1. It will add up to 3. So let me keep it equation third. So again, if I go for k steps, there I have found the pattern. And the pattern is what? So for kth step, I will write t of n will be looking like what? T n to the power 1 by 2 power k plus k. This will be for kth step. Okay, now what was my initial recurrence was that, I will write it here again to, it was 1 when n was equal to 2, n was greater than 2, it was equal to t of under root of n plus 1. So my t of, if I substitute n equal to 2 here, okay, if I put 2 in place of n, I will get t of 2 here. Okay, okay. So from equation k, I will see that if I had to make this equal to t of 2, if I had to make this term equal to t of 2, what does that mean? I had to substitute n power 1 by 2 power k equal to 2. This is what it means. Because why I am doing this, I have been doing it continuously in case of dividing function decreasing, because I know the value of t of 2, that is equal to 1. So to make this term, to remove this t term from this equation, I should be able to put the value of n power 1 by 2 power k equal to 2. So if I keep it equal to 2 power 1, I think, is it? No, I had to do one more assumption here before doing this thing. That assumption is that, let me take n equal to 2 power m. This is assumption number first, because we are changing the variable. That is why its technique is known as change of variable. Assume n is equal to 2 power m. Let me remove it. So when we are changing the variable, this means my m will be equal to log n to the base 2. Because I am taking n is equal to 2 power m, taking logarithmic on both sides, that will give m is equal to log n to the base 2. So if I substitute this value n is equal to 2 power m in this equation, what I will get in place of t, and it will be equal to 2 power m. Okay, this will result in t, and here you see this is n. N will be equal to 2 power m, means in place of this n we have to write 2 power m, 2 power m, and already it is having the power 1 by 2 power k. This is how it will look, plus then this k will be here itself, no change in it. So this will result in t 2 power m equal to t, this will become 2m divided by 2k plus k. Now this has become our standard form. Let me denote it by any name k1. So my original recurrence was t of n is equal to. So what I need to focus now, I need to bring it in a form where it will be equal to t of 2. Yes, in place of n, I need to substitute n is equal to 2. I know that that is equal to 1. So if I have to get it equal to, I had to make this one, this thing I had to make equal to t of 2. That means I had to assume one more thing, that this 2 power m divided by 2 power k, it should be equal to 2, because I am substituting 2 here in place of whole of this value. Yes. So if I take its power equal to 1, that means m divided by 2 power k is equal to 1. And moving forward, this will become equal to m is equal to 2 power k. Okay. And k will be equal to log m to the base 2. And my m was equal to log n to the base 2. Okay. Substituting the value of m in this equation, it will become equal to log of n to the base 2. Okay. Actually, I have shared this material to you in the group also, but I know it will become hard to understand it there if we don't discuss it, because I myself found it very difficult to understand. Let me be very honest with you. Not this one, I mean the previous ones, to find how to solve it to all this. It was kind of hectic. There is very, there I could not get so much material also. So there is one more recurrence of the similar type, and this will be a sort of assignment to you guys to solve it. I will stop it here. The recurrence is just like the same. And this change of variable, please remember it, change of variable, it is also known as the root function, because in this we change the variable whenever the recurrence is called using the under root function. No, neither dividing nor decreasing. When there is a root function, you should keep in mind I have to change the variable. How many times I don't know. That depends upon the particular recurrence. Okay, but at least you should attempt to solve it, so that your examination checker will come to know that you are up to the solution, or you know how to solve it. 2t under root of n plus log n. This is one more root function which needs to be solved using the same change of variable method. And I will write down its solution also here. What will be its solution is log n into log of log n. log n into log of log n is its solution. So try to make the necessary variable changes inside it and using the same method which I used for the first one. And you will, this is for sure, you will have one doubt in this while solving it while trying to search for different solutions on the internet. You will have one doubt in it because same doubt I also suffered. Okay, and we will discuss it tomorrow in the class then. So this one will be sort of assignment to you, and tomorrow you will discuss it with me, and I will then stop this lecture. Okay, and we will meet tomorrow.